3 years ago, I started looking at every piece of storage that I could find, whether that be open source, closed source, appliance, or software defined, trying to find a solution for JASMIN's ever-growing demand for high-performance storage for environmental data analysis. In this talk, I'm going to talk a little bit about what the requirements are for that. So both what we're driving us towards object storage, which is the title of the talk here, what the reasons for high performance. I'm going to talk a little bit about an at-scale proof of concept analysis that I did about 2 years ago now, and the results of that, which drove us into the requirements for our procurement exercise and the results that came out of that. But first off, what do I talk about when we're talking about environmental data analysis? So JASMIN is the UK's platform for all of environmental data analysis in the UK, and these are some examples of the kind of things that we're talking about. So this, the top left-hand picture is this one here. This is from the Wellington earthquake a couple of years ago. And this is from a group, Comet, at the University of Leeds, whose infrastructure runs on top of JASMIN. They're taking Sentinel data, which is a European Space Agency satellite mission, looking at every every earthquake region and every volcano region on the planet in near real time. So for the Wellington earthquake, they were able to tell the authorities where the worst case landslips were, which actually interestingly was not where they thought they were. And then the other picture here is from the subsequent Italian earthquake region, and this is just looking at the before and after stress in the ground. The satellite is able to measure down to 10 centimeter resolution from space. So that's one kind of environmental data analysis. The other things that JASMIN does is climate analysis research. So this is from a 600 terabyte data set that was run on Hermit, one of the Prace machines in Germany. Ran for about a week for the whole of a climate sim. So that's all the oceans, all the atmosphere, all the land. For a 10-year simulated run. Data set was brought back to JASMIN, and analysis was done on that data set. Specifically, they were looking for where the hurricanes come up from the African region through the Caribbean and into the UK. So that's picking out analysis from there, but JASMIN also holds about 40% of the data that went into the last IPCC climate change report. We're committed to holding about 60% of the data that will go into the next high resolution one. And most of the the IPCC climate change report is about model into comparison. So looking at one person's view about how the climate's going to change compared to another one. And that's really where one of the prime leaders of JASMIN. But those are not the only kinds of things. We also do citizen science projects. So there is a huge amount of data. If you've ever seen any calls to go out into your back garden and look at what kind of birds you see on a particular day, that's a citizen science project. But there's a lot of observational bias in that data. So unsurprisingly, when you go out, it tends to be during the day. Some birds come out at night. If it's a sunny day, different birds will come out, but you might want to know what the birds that come out when it's wet. So there's a lot of observational correction, and there's a ton of Monte Carlo simulations that go into that. And I'll talk about how that, on the next slide, how that's run on JASMIN. And then there's a whole pile of virtual environments that sit on top of JASMIN, both to analyze data and to present that out to the outside world. We're currently running about 90 different projects, I think, and as I'll show in a second, about 1,900 different users. So, unsurprisingly, because this is environmental data, some of it's quite high profile. The citizen science project that I was talking about earlier, turn turned itself into the UK Biodiversity Indicators report to government. That's from 2017, but there's another one in process now. And the work that they did on JASMIN allowed them to analyse thousands of species, not just birds in the back garden, but also fish, insects, and at scope and complexity that was far in advance of what they've been able to do on their previous systems. The Comet CPON people, as you can see, they've had a lot of news stories, unsurprisingly, because this is quite high-profile stuff. As I mentioned, they use the Sentinel data, which JASMIN is the UK data hub for the Sentinel missions. That's a terabyte of data download from space every day, and we're committed to hold all of that data. Comet's quite interesting because they use all of the pieces of the JASMIN infrastructure. So we call JASMIN a super data computer. So we have significant high-performance storage, but actually relatively small amounts of cores. So about 10,000 cores now, but about 44 petabytes usable capacity of high-performance storage. So they use our batch computer, they use our cloud infrastructure to both do the analysis and present the results out. They have relational databases inside the infrastructure, so they're using all the individual pieces of JASMIN. And other things that JASMIN does, some people, if you're interested in this kind of stuff, there was a story from November last year. Some parts of JASMIN are contributing to the PRIZE project, which is giving farmers in sub-Saharan Africa alerts from crop pest insects. So if you get a plague of locusts spreading across fields, we can tell from space, from those satellite missions again, we can predict where those insects are going to go next, and the farmers in the field can actually subscribe to alerts. I'm not quite sure what you would do against a plague of locusts once you get that alert, but I mean, that's not really my problem. Okay, so those are the kinds of things that is environmental data research, and JASMIN is kind of seen as the missing piece. So obviously we have things to measure things with, so we have satellites, and we have computers to run big simulations on. I mentioned Hermit, but obviously JASMIN has links to the machines Archer up at Edinburgh, and also to the Met Office's supercomputers down at Exeter. We have the satellites. We've obviously got the NERC has the so NERC is the Natural Environment Research Council, who fund most of JASMIN. They have aeroplanes. They also fund the Boatface boat, which is another source of that data. But there was no, up until JASMIN was invented, which JASMIN's been stood up for 7 years now, 2012 we came online. There was no one piece to actually do the data analysis, to bring the measurements and the simulations together, to be able to compare real against simulated and compare simulated against other simulated. So that's where JASMIN fits in. So as I mentioned, I'm going to talk a little bit about why we think object stores are important for us and why high-performance object stores. Object stores in the past have been thought of to some extent as very like tier 3 kind of storage. So there's almost like close to tape. But we're going to try and use it for high performance as our tier 1 storage, and I'll talk about why we're going to do that. I'll talk about the POC, talk about the two technologies that we ended up deploying, which is QuoByte and Caringo, and then a little bit about the heart of the network that actually drives some of the results that we've actually got. So what's the thing that are driving us away from a file system? So when we first started, we had a few hundred users. An HPC system tends to be, a supercomputer tends to have, tens or a few hundreds of users, and then PhD students come and go. The numbers wobble up and down a bit, but it's usually fairly static. JASMIN, in my experience, has been incredibly unusual that it's, once it took off, people have been registering for it and they haven't gone away. So we've gone from a couple of hundred users to 1,900 users and counting. We're registering about 20 new users a month. And each one of those users come on a shared file system, so we mount all of our storage at the minute, which is a POSIX file system, across all of the probably 1,200 virtual machines, 1,200 mix of virtual and physical machines. And each one of those in a shared file system comes with a UID, comes with GIDs for the individual projects that they're involved in, and actually managing and keeping track of that is a huge overhead. And when you add in the cloud and the things that Stig was just talking about, obviously you've got root users, and if they're mounting those file systems, they can just go user add, and those UIDs will then just clash with all of this. So it's a right mess, and it's really difficult to handle. And the size of the data is increasing as well, so the number of projects that we're looking at. This is a couple of projections of the size of the data that we're talking about. The one on the left-hand side here, we're at 2019 right here, and this was a projection that was done in 2011. We're at 2019 now, and if you look at it, JASMIN's has the capacity to store about half of that data that was projected. The right-hand side graph here actually comes from the Met Office, and their projections for when you're going to get through to exabyte levels is early 2020, so that's only 3 or 4 years away. So JASMIN, we're targeting getting to about 300 petabytes of usable capacity on disk in the next 3 to 5 years. And that's not unreasonable when you look at these two estimates. And that's driven by the number of projects and the numbers of users. So as I see down here, we've got 400 different storage volumes. Most of those are associated with different projects. Obviously, the users come and go, and they've got different data sets that they overlap. So we've got huge numbers of users, huge numbers of projects and counting. But we also have an interesting thing with the way which the data is actually stored, and I'll show on the next slide why these two file formats are important. So most of the data on JASMIN is stored in NetCDF and HDF format, and both of those are file formats for storing data where there's there's an index at the front of the file telling you what's inside it, and then maybe some X, Y, and time series data that's actually stored in it. And sometimes when you actually want to go through that data, sometimes you're only interested in the data at a particular location in the file. So you read the header, and then you skip through the file to get to the data. And then you might skip through it again to find some data that's further down it. And that's a terrible pattern for reading files off a high-performance file system. So there are a couple of projects to try and break that out into. One is the S3 NetCDF, which is the left-hand slide. My colleague Neil Massey has been working on, and this is one where those individual chunks of data in the file are broken out into individual objects. So you read the metadata, and then that tells you which of those chunks you actually want to get. So you go straight to the object that you want. You don't have to skip through the file in order to find it. And the HDF group, commercial organisation, they have a slightly different model, but effectively is doing the same thing. So breaking up those huge files. And these files, as we'll see on the next slide, they're gigabytes now, but they're projected to get to terabytes. So we want to get rid of this serial skipping and breaking those up. Another part about the files that you see on JASMIN is that on a POSIX file system, they very often have this pattern where you get a directory with the year, and then you get 12 directories with, guess what, 12-month date on them, and then you get 31 directories underneath that, and then underneath that you get a pile of files which, guess what, have a timestamp on them. And all of that whole hierarchy of directories, all it's really telling you is the metadata of when the data was actually taken. Now, wouldn't it be just much easier if you took that piece of information and you stuck it in the metadata of an object, and then that would get rid of the entire hierarchical file system and all the stuff that comes with that. So I mentioned earlier about the size. So if in the bottom right-hand, bottom left-hand, you can see that these are these two file formats. The one at the top is NetCDF. That's our biggest majority of the files holding, and then it's followed by HDF. And then there's a pile of other things as well of different varieties of storage. So we took these kind of plots, and we used these for our proof of concept for object stores to find and it turns out to be quite critical, this choice, which I'll talk about later. We chose a 2 gigabyte file object for the POC to uses our kind of test file size. So why high-performance object stores? So the JASMIN workloads are an interesting mix. Some of them are the HPC parallel workloads that Stig was just talking about, but actually that's very little of it. Most of it is actually high throughput. It's taking petabytes of data or hundreds of terabytes of data split into these individual files and firing off and analysing each one of those files in a huge chunk. We quite routinely see people submit 300,000 jobs into the batch cluster part of JASMIN, but here there was a spike of 1.4 million jobs. That's all from one user. We've actually seen 10 million jobs sitting on the batch queue, pending, and the red line, by the way, at the bottom is the running jobs, because the number of cores that we had at the time, this is about 4,000 running, is very small compared to the number that are being submitted. Now, as you can see, we get through them pretty quick, and that's because the workload tends to be read the file, pull the header, seek to the piece of data, pull it off, stick it into, maybe there's a piece of statistics that's going on. So each individual job is relatively small, and to some extent that's more of a high throughput workload. But there's a lot of it, and it's all I/O, and most of it's read I/O, which importantly is the key here. We're also reading a lot of that data. So this was taken about a year ago, but you can see this is a smoothed out monthly mean of the amount of data that we're reading through from JASMIN. It's not unusual to be reading a petabyte of data a day on a lot of days in big spikes. As I said, we have about 250 to 300 10 gigabit nodes in those. We've just, as part of the JASMIN 4 phase, which we're talking about here, we added another 225 gigabit connected nodes. But this data isn't all one project, so you've got to remember that you're actually mixing different people's workloads here as well. It's not all one application. So those are the sort of things that are driving us towards object stores and the high-performance object stores. Having looked at all of the storage requirements, we ran a full-scale proof of concept. We were looking for something. Obviously, we were starting at a base of about 12 petabytes of data and expanding into that kind of 50 to 300 petabyte region. In my team, the systems team, there's only myself and 2 others. So we have to have something that's easy to manage, doesn't necessarily require a huge amount of expertise. We don't have a dedicated storage person. Up until that point, we got away with about 10% of one person looking after the file systems that we used to date, and we wanted to continue that into the future. JASMIN is funded very much capital-based and not very much OPEX, so that's quite important for us. So there were a number of objectives for this thing. We needed to be able to comprehend multiple rounds of procurement. Money comes to JASMIN in anything from a few thousand pounds right the way through to a few million pounds. So we ideally, some of those projects who come to us and say, well, can you put in 2 or 3 terabytes of storage? We want to be able to go out and buy a few disk drives, plug them in the cluster, and say we're done with that upgrade. But likewise, if NERC come to us, as they did do for JASMIN 4, and said, can you spend £8 million? We want to be able to comprehend that. But also, when you're doing that, we're also doing that through a public sector procurement exercise. So we can't specifically say we must buy those pieces of hardware. We can only say, generally, we want a piece of storage that has these characteristics on it. And that means that the things that fall out of that, those kind of things, can be any mix of hardware. You can be HP, Dell, whatever. So we need a system that is capable of effectively taking in as much bits of hardware as we can get in as small as increments. For the reasons I've just talked about, we wanted S3 REST APIs, or at least a REST API. It doesn't have to be S3, although that's what we focused on. But critically, we need something where we either have a custom file client or NFS that can talk to the same objects as the REST API. That's pretty critical because obviously we're not there right now with the APIs, but we need to move people in a direction. So we've got people on workloads who are used to POSIX file systems, and we need to move them over the next few years onto high-performance object stores. But to do that, they need to be able to operate on the same objects. We don't want them copying data from a file system into an object store. That's just duplicating the storage and duplicating the cost. So then there's the performance. So from our existing parallel file system, we were getting about 70 megabytes a second per spindle. And spindle here is critical because we're not talking about high-performance SSDs or anything like that. It's the cheapest that we can get away with from more spindles. So I kind of figured that if we could get a system that was cheap, did about 50 megabytes per second per spindle, that was great. Anything about 40 megabytes, well, okay, that's not too great. But anything that was sort of 60 megabytes a second, 70, 80, more than that, we'd be super happy because that would be about the same performance as we were getting from our traditional parallel file system before that. And I've talked about the total CapEx versus OpEx thing. So we bought a 2 petabyte cluster, which was composed of a mix of Supermicro and Dell hardware. Doesn't really matter what the details are here, but spread over 10 nodes. Critically, the important thing was it was about 400 spindles worth. So we're kind of looking for something that's going to give us performance over those nodes, and it must be erasure coded as well. And interestingly, we actually managed to find some pretty good results. Actually, I was pleasantly surprised. I was kind of feeling that we were going to find some things that were going to be down that 40 megabytes a second per spindle for erasure coded things. But the system on the left from one particular vendor is for software defined file system. Came out, and this is, by the way, is completely untuned. This was me doing the install on the proof of concept cluster and just figuring out how fast we can make it go without too much work doing on it. The one on the right hand side is from an object storage vendor, and that was about 70 megabytes per second per spindle. But crucially, when you actually work this out for those rates, that's 15 gigabits a second from 27 hard drives in a particular chassis. So you're already breaking most object stores. They tend to come with a lot of disk drives and a 10 gig network on the back. The cluster, which you may have noticed on the previous page, every single node had a 40 gig NIC on it, because what we're trying to find out was what the software could do, not what the networking could do. So when you're spinning up these 15 gigabits a second, that kind of proves that you definitely need a 40 gigabit network. And very interestingly, on vendor B, in their labs, they'd never seen these kind of data rates before. So they had it actually, very interestingly, by sheer coincidence, they had very similar hardware to what I did in our proof of concept, and I got 40% more performance than they'd ever seen in their lab benchmarks before. And they were kind of targeting doing traditional object workflows, and simply by sticking a fairly sophisticated network on the back with very high throughput, and we'll talk about the network a bit later, we were able to get some significant data rates. But that doesn't always work. There were certain vendors where it didn't work quite so well. And interestingly, that tells you about the 2 gigabyte objects. In this particular issue, this particular vendor, they had always assumed and always been presented with object file systems, which were, with objects which were of the orders of tens to hundreds of megabytes in size. Now, we're trying to take an object that's 2 gigabytes in size and trying to read it. And in an erasure-coded system, what they were doing was sucking the erasure, all the pieces for the erasure-coded file, pulling it into memory, and then sending off to the client. And unsurprisingly, if you do that for one file, that's fine. But if you start doing it for 10 files or 100 files, guess what? You run out of memory. And that's exactly what happened here. Now, to give them their due, they managed to turn around a fix very quickly. But it was kind of scary that these guys have been in operation for 6 or 7 years at this point. And this was the first time they'd ever actually seen this kind of bug. So Anyway, so we did this proof of concept. We had some good learning. We went through a full public sector procurement for this, 8 million. If you ever tried to do that, I can tell you it's not easy. But we came out with two winners, Caringo and QuoByte. Caringo is traditionally an object store which has an LFS interface on it. QuoByte is a file system which has an object system on top of it. You can see that we've gone significantly, so 2018, this bit of JASMIN 4 that we're talking about here, we've increased our usable capacity by quite a substantial amount. You can see from this, our previous file system vendor was Panasys, and they are a fantastic company, and we expect to be working with them for a long time now, but they didn't meet the requirements. They don't have an S3 interface left. Sorry, they don't have an object interface to their file system store. They're very much a parallel file system. But there are requirements for that elsewhere in JASMIN. So there are a number of other things which we got out of both Caringo and QuoByte. One of the key things was this it's a detail called a callback port with Panasys, which made it incredibly difficult to mount the parallel file system into a machine that's part of our cloud. It required the root owners to actually know things about firewalls and stuff like that. And it was horrible, but we've removed that. So QuoByte. As I mentioned, QuoByte is a file system with an S3 interface on top. We have installed the world's largest, well, actually this was back in November when I did this talk the first time, and at the time it was the world's largest capacity deployment of QuoByte. I think that Yahoo Japan may have a slightly bigger one, but they are doing replicated rather than erasure coded for a number of reasons, which we can go to the QuoByte website and see a very interesting presentation about how they're using it. For us, critically, we actually managed to end up, because of the complexities of the procurement, we ended up with a Dell Supermicro split, and that's been extremely interesting, but it also means that we can see side by side the performance of the two things, and it also gives, going forward when we do more procurements, we can see that both of them actually work. This thing's been benchmarked at 220 gigabytes a second, and that's crucial. It has a theoretical capacity of about 270 gigabytes a second. We haven't quite pushed it to that. There's a number of things around there, but you can see we're into that kind of 70 megabytes a second per spindle, which is up there with our traditional parallel file systems. And one of the nice things for us as an infrastructure provider is we actually get these interfaces into what the users are doing. So we have on the main console for QuoByte the ability to actually look at who's doing what, on what machine, with what user, and that's incredibly powerful for quickly finding out where things are going wrong. The other thing about this is those kind of levels of gigabytes a second, they require lots and lots of networking performance, which I'll talk about in a second. Caringo, as I'm running out of time here, Caringo, as I said, is an object file system. In our implementation, we have 400 gig connected S3 gateway nodes, and all of the traffic is passed through that. There is a white paper on the Caringo website if you want to go and check it out. They managed to get about 64 megabytes a second per drive in those, and again, that's comparable with the kind of 70 megabytes a second per drive we were getting from our parallel file system. So that's really powerful as well. And critically from these two systems, we also have a multi-tenancy thing. So along with all of the other requirements, multi-tenancy is key for JASMIN. We talk about all of these different projects, and because of the way that the tenancies are implemented, it means that we can present interfaces from both Caringo on the right-hand side and QuoByte to our users, and linking those to our OpenStack cloud, so that users have got a completely, in print, we're not doing this quite yet, but we will be there fairly soon, to allow users to deploy their own volumes and manage their own users and their storage. In the heart of this is the networking. Although this diagram is incredibly difficult to work out what the hell is going on here, the key thing is the bit in the middle, which is the high-performance network. This is the bit that makes all of that performance actually work. I mentioned that Caringo had never seen a network before that looked like this. It's low latency, non-blocking network, so it doesn't matter where you go. You are not going to lose any bytes, or at least that's what you'd think. So to give you some kind of flavour, we run a data centre network. This is actually our JASMIN 2.3 network, which was sufficient up until about 2016, 17. We ran out of ports about 2 years ago. This is 1,500 ports at 10 gig, non-blocking. And we had to go to a 5-layer CLOS tree. So that's one of these blobs at the top here. And the bottom is effectively what you've just seen on the previous page. This is actually only looking at half of what we've got for our 5-tier CLOS. We actually have 16 3200 gigabit switches in the central spine, which is the bit in yellow here. And you would think that with all of that bandwidth going, you would never have a problem with congestion. This is just showing with the, we've got lots of compute on one side, lots of storage on the other side. And when you just do the comparison, you say, well, the storage that I mentioned earlier is about 2 terabits a second coming out the storage. I've got 4 terabits a second on my compute, and so I should never get blocking. But unfortunately, the storage can actually swamp an individual client here. So that's a real problem. And if that 220 gigabytes a second I was talking about from the storage engine we could only maintain that for a few minutes. Without doing anything about it, and that's because the packet buffers in the switches were just filling up very rapidly, and once the packet buffers were filled up, the system then fell over because packets were getting dropped all over the place. So we ended up doing something very interesting from a networking perspective. I don't know if this stuff actually means anything to you, but in an InfiniBand network, traditional kind of things, you'd be doing RDMA, and traditionally you have to do priority flow control in order to manage those kind of things. JASMIN only has traditional TCP Ethernet networking deliberately. We don't have any InfiniBand, and that's a management thing. So we only have one network to worry about. But we can't. We're not running Rocky, so we can't prioritize the traffic. So we had to find another way, and we actually went back to a protocol which ECN, which kind of ran out of favor about 10, 15 years ago when it didn't work very well. And as far as I'm aware, this is one of the first places that actually brought back ECN for priority flow control, effectively communicating between the client and the server to tell the server to back off when the port on the switch is getting overloaded. And having implemented this, we were able to sustain that 220 gigabytes a second with virtually no packet loss at all. So in summary, key things from this, we have a single hardware environment, which now as we can actually take the same spec and run it across different pieces of hardware. But even with these things, there are dragons. We've talked about the issues with some of the storage vendors and the way in which their software kind of falls off. We've talked about the ECN. An object file system can behave at parallel file system speeds, so that's great for us going forward. But there are caveats in doing that. But the network needs to match the bandwidth and the latencies in order to achieve that. So there's some fairly sophisticated things. But given all of those things, and given the CLOS tree networks that we've put in place, we're now on the road to high performance object stores. And this is my last slide. So so JASMIN's now on the road to high performance object stores. We've got that link between file systems and objects, and now we can actually start migrating the users towards the advantages of using object stores. So thank you. Any questions? John.
That's a question question and a point. You said you weren't going to use Parnassus anymore because they don't have an SD object gateway. Absolutely accepted. But I'm sure you're aware that Parnassus now deploy commodity hardware. Did that make them look a bit more attractive to you?
As I say, we're not going to. So we still need a parallel file system. There are places where. So some of our users are using MPI-IO. Okay, so MPI-IO, guess what? That doesn't work very well with an object file system, right? So for those kinds of workloads, you need a parallel file system. So yeah, the things that Parnassus are doing is fantastic, and obviously they've moved on a bit now. They're doing some good work. But we needed an S3 interface to the storage in order to migrate our users down the path, and currently they don't have it's on their roadmap, but it's a long way down the line yet. So, yeah.
One observation: this isn't an observation from JASMIN. I've seen many projects where people set up a parallel file system and say to the user, "This is Scratch, high-performance Scratch files." I'm thinking BGFS actually.
Yeah.
And then it ends up being used as a long-term
data
storage. It fills up when it's full, and people won't migrate the data off it.
Yeah. So we delete it.
It's a real management headache, and we've got to move to these expanded West3 object stores. We can't keep standing up these expensive.
Yeah. So JASMIN has a thing called a file transfer cache, which is like a managed big data cache, and you get a quota on there for a certain period of time, and if you don't move the data off, it gets deleted. So that's how we're doing it. Sorry.
It's also worth noting as part of the same point that part of the same, I work for a different part of STFC that collaborates closely with these guys. We're also helping our community and trying to develop software to ease the transition as well. So that's an important thing to focus on as well.
Yeah. Sorry.
Yeah, I would like to comment that you've been doing a very impressive proof of concept and a lot of detailed investigation. I was just wondering that, say, ignoring you have to go through the public procurement or you have to do the POC, start over again from today. Would there be anything you want different?
What in the requirements or? I don't think the requirements haven't changed. I think what's happened in the 3 years since I first started doing this is, unsurprisingly, there are a lot more storage vendors in the market than there were even when I started looking at this 3 years ago. And so there have been some innovations, and I think everybody's been responding to those requirements, I think, quite well. Obviously, when we go back into getting from where we are now, 44 petabytes of usable capacity out to 300 petabytes, we'll be going back through multiple rounds of public sector procurement. And to some extent, the reason that we have multiple storage platforms is it gives us the option of actually moving from in terms of software, to move from one to the other as things balance along. And because we're focusing on the S3 interface, which is relatively common, although there are some differences between different people's S3 implementations. In principle, it would allow us to go, well, you guys over there, you're not doing what we need to do. We're just going to stand up a new thing that's got some different kind of, but it's still S3 in the background. So this is sort of the other driver of actually sticking with S3 and not one of the proprietary REST APIs. Yeah, no, I don't think there's... our requirements, as you've sort of seen here, are relatively generic. We've not tried to push to anything very specific. We didn't say anything in the procurement about the specifics of authentication and authorization inside the S3 object model, which is obviously is quite important. So we didn't push that too hard. Probably next time around we'll be looking at that some more. No, other than that, I think, yeah. Yeah, it's quite hard. As I say, I didn't think we were going to make it when I started 3 years ago. It's you really have to get out there and look at. Actually interesting, the two solutions that we've actually ended up with. One of them had only just come out of stealth when we first started looking at it, and the other one, Caringo when I talk to people about Caringo, nobody ever heard of them, although they've been around a long time and they have some very mature technology. Yeah, you only find that out by getting out and talking to people. It's quite hard. So.
I'm curious whether you looked at how far you can push that.
Yeah, yes, that is another whole talk, right? And that's kind of why I've said I felt a bit of a fraud standing up here, because obviously the solutions I've talked about are commercial solutions. Ceph wasn't in my testing. Ceph wasn't fast enough. It doesn't have this ability to read from an object model, and if you're implementing CephFS, the two things, you can't point to the same objects at the same time, which is critical for us. Again, at the time we were talking about this, CephFS wasn't even at version 1.0, so it didn't, and implementing a file system is not an easy thing, and I think that's why CephFS was, kind of like in beta for a very long time. So that would have been a huge risk to have actually gone into that. The QuoByte guys, although they'd only just come out of Steph when we talked about this, all the developers we actually knew from the ExtremeFS project, so that they'd already been through this round once before. And there were issues with erasure coding at the time that we were looking at this 2 years ago. Erasure coded Ceph clusters were a bit of an oddity. I understand that at RAL we were running the largest erasure coded Ceph cluster, and I think we still are. Or not? Yeah. So, but at the time we were talking about, the largest publicly known was the one that we were running, and that I think was 8 petabytes. Well, as you can see, we've just bought 40 petabytes, right? So it had to work, and it